continuation of the webinars of the AFRONE. This is the second round of the AFRONE mentorship, second cycle of the AFRONE mentorship program. And the webinar is open to all AFRONE mentees and also to non-AFRONE members. In this session and the next one, which is going to be scheduled on next Thursday, same hour, we're talking about one of the sciences of the future. This is the session about artificial intelligence and its use in dentistry and oral health. The two sessions are like in a continuation. They complement each other. So we'll begin the discussion today and we'll continue on Thursday. The session is recorded and will be posted on the AFRONE YouTube channel. Some housekeeping rules, please. Please mute your microphones during the presentation, and feel free to ask questions on the chat. Also, at the end of the presentation, there will be a discussion where you can share thoughts or ask for clarifications or raise points. So either on the chat or at the end of the session. Now I would very much like to introduce our speaker for today. Our speaker is Professor Marwan Torki. He's professor at the Computer and System Engineering Department, Faculty of Engineering at Alexandria University. He's specialized in AI and computer vision and has obtained his PhD from Rutgers University in the USA. Professor Torki has more than 100 Scopus Index publications with more than 3,700 citations. He is a recognized speaker at national and international conferences. He supervised dozens of graduate students at Alexandria University towards their postgraduate degrees. Professor Torki is the founder of the NIGHTS Lab, which trains and mentors fresh graduates and early career researchers in computer engineering. He provides active consultations for many computer vision projects at the Applied Innovation Center of the Ministry of Communication and Information Technology in Egypt. It's our pleasure to welcome Professor Torki. Professor Torki, the floor is yours.
Thank you very much, Professor Maha, for the introduction. And I'm very pleased to give you this webinar. Our webinar talk will be about pipelining AI tasks. So I will start the presentation. The presentation is divided into two sections. The first one about the pipeline of AI tasks, and then I will go through some other section about how to formulate your problem into a pipeline of AI. Okay, so let's start at the very beginning by defining our objectives in this section. It's about overview about the pipeline, what is meant by pipeline. And this will be shown to be very useful to you if you are thinking about an AI problem. Then you have to think carefully about the pipeline and its components, because at the end you will find this modularity will help you a lot to define your problem and solve your problem in a modular way. And then we'll think what are the components of this pipeline. We'll go through these components. And finally, we'll decide what are the input and output specifications for your task. Because at the end, you would like to define what is your task and how I'm going to solve this task. Okay. So what is pipeline? Pipeline is a structured sequence of processes or steps. So for example, if I'm telling you what are the steps to make a juice. So what is your steps? So you define your steps in step number 1, step number 2, step number 3, step number 4. At the end, you will obtain the juice. So the pipeline is to how to think in a structured way, in a sequence of processes that will give you the result that you would like to get at the end. Okay, so it is multi-step because we are not solving one thing that is doing everything in the world. We divide the problem into multiple steps, and every step can be customized or replaced, and that is what we refer to as a modular approach, because now the modules can be replaced or modified, which makes it generalizable to many problems. And also the good thing about the pipeline, it is adaptable. You can use it in different tasks. For example, you are concerned about the diagnosis, so you can make your own pipeline, but using the same steps. Some other researcher might want to have a segmentation task, for example. So what will change is some blocks will be removed or changed or adapted to different tasks. So this will be clear in the next few slides. So this is what is the pipeline. So what are the stages in our AI tasks? We start at the very beginning with data collection and the preparation, and we call this as a pre-training steps. And then we will go to the training, the models, which is a very lengthy and very important tasks, and we call it a training loop. Training loop, it means that it doesn't end at one step. It has some recurrent steps. So you are doing these steps recurrently until you find you find your objective achieved. Okay, and then you do the evaluation, and then at the end, after you finish the training loop and made sure that your system is working as you are expecting, you do the validation and the visualization to report your findings. So what I'm going to do is to do some overview on every component of these components of the pipeline. And in the next section, I will give more detailed description for these parts as well. But the first section is going to the overview to make sure that we can cover the whole story from a high level. So, for example, what is what is going to happen if you are going to, for example, work on segmentation for the ion, the nerve. So, for example, you have your own data, but the data that is coming from multiple sources, maybe different CBCTs, scanners, and so. So they have some ranges that are different, or they are having some resolution that is different from one machine to another machine. So one very important step before doing anything is to make the data more cleaner. So one of these modules is to do a pre-processing module to make the data set or your own data that you are at the end you are going to train a model, for example, to learn where is the nerve, where is the ion nerve. So to make this process easier, to make the training happen, then you have to do these pre-training modules. One of them is called the pre-processing. It will transform the raw data into a clean, structured format suitable for model input. So the next step will be to check if you need an augmentation technique for your data or not. We know in the medical domain, it is very hard to find a very large data set. It's very hard to find large data sets because we are working with human beings, so, and it is not easy to find, for example, 5,000 cases to train your model on. So obtaining data is very crucial for any AI algorithm, and we will see in a later step why this is very important. If you don't have very large data set, then your chances of obtaining good results will be lower than you would like to have. So one way to increase your data set is to apply some augmentation techniques. And by augmentation techniques, we mean that we can apply some geometric transformations or maybe some photometric transformations. In the CBCT, the photometric transformations are not very clear what to do. But for example, if you are working on RGB images coming from intraoral scanner or RGB images coming from extraoral cameras, then you can do photometric transformation to change the colors and so on. So the augmentation is important if you don't have enough data, and usually it is done in a pre-training step. But you have to be careful when you are applying the augmentation, because there is very important mistake that is happening in many cases, that you augment the data, then you make many copies of the same sample, but with different transformations, as you see in the slide, but they belong to the same object. So it means they cannot be separated in the training. So they have to be in the same training set, not to distribute them among the training data and test data. Because if you distribute them among the training data and test data, then you are cheating, because there will be a data leakage for the labels in this case. So the augmentation is important, but you have to be careful when you are doing this augmentation. The first thing to think about, if you are going to solve a problem, then you have to have a large enough training data. But if you don't have a large enough training data, then you can do this augmentation. But if you do the augmentation, you have to be very careful so that you don't leak the labels between the training data and the test or validation data. Okay. So the first step in the pipeline was pre-training, and we showed some examples of what can we do for pre-training, either pre-processing, doing feature scaling, or unify the resolution of the images or the scans, whatever. And also the augmentation is very important. Now, the most important part is the training loop. The training loop, it consists of multiple iterations, and every iteration passes through the whole data set, the whole training data set, and we call every pass on the whole training data set is called an epoch. So the iterations start with data loading, and then model inference, and then output generation, and then loss calculation, and then optimization. So this is very and I mean, this is very superficial description of what is happening inside the training loop. But to make things clear, we will go through every step in this iteration. The first thing is to write the code for data loading. Data loading means what? Data loading means that you are preparing the data into the same format, into the same size, into the same resolution, and divide them into batches. The batch might contain more than one training example. And the batch size depends on your available hardware. So for example, if you are rich enough to provide strong hardware, then you can increase this batch size. But if you don't have this luxury and you have limited resources, then you reduce the batch size. So the batching is used to better utilize the hardware available to the researcher. And for example, in this case, we divided the training data set into 3 batches, and every batch contains some training examples, and we might have more than these training examples. So that we might have more than 3 batches, but this is just for illustration. Once you prepared the data and kept them in the same format and same resolution, same sizes, and so on, then you do this model inference. So what is meant by model inference? Okay, at the very beginning, you define your model, but you might not have the best model at this moment. So the training loop starts with an initial model, which might be doing mistakes a lot at the very beginning. And then what is the job for the training loop is to learn how to make better predictions. So at the very beginning, you do this model inference and create some predictions. And these predictions, okay, that's fine. It does many mistakes. And once you compute these predictions, you generate the outputs and check the output generation that you have obtained and compute how many mistakes you have done. And we quantify the quality of the model by computing the loss function. So the loss function is different between different problems. The loss function for classification problem is different from loss function for detection problem, and also it is different from some segmentation task. So it depends on your problem on hand. You define your loss function and measure the quality of the predictions that you obtained from the model inference. And then there is an optimization algorithm. The optimization algorithms are doing the search for you. They search for the best model parameters given the training data, given the current loss. The optimization techniques will give you a better model than the current model. So what's going to happen again? And then you do the loop. The next time you will have a better model. You go back, do the model inference, create the output, compute the loss, optimize for better weights, and so on and so forth until you feel that your model is trained enough. How do you feel that the model is trained enough? There are some heuristics that can help you. And also you can observe the loss function. And once you see there is no improvement in the loss, then you can stop. And there are many other details in the system. So after you are good enough with your model, you take this model and apply it on your validation data, for example. But here it is written test data, but it should be validation data. I will tell you some difference between what is test data and validation data from the point of view of machine learning and deep learning, because there might be some differences in your context in the dentistry. So let me tell you this is because this is important before going further. Suppose you have, for example, 500 cases and you would like to segment the IM. Then the first thing to do is to do the training data split. To split the data into training set, validation set, and the test set. The training set is used to learn the model parameters. The validation set is used to tune the hyperparameters. And the test set is to test for generalization. So the validation set gives you the opportunity to fine-tune the hyperparameters. But the training loop is giving you the opportunity to optimize for better weights of the current hyperparameters. But if you'd like to test many hyperparameters, then you have to use a validation set. And the most important thing is that the data that is used in the training set should not be mixed with the data that is used for validation or that is used for the testing. Because if you train a model on some sample and you test the model on the same sample, you are going to get good results. But if you are going to test for the generalization, it is always better for you to test for unseen samples from the training data. Okay, so then you observe the evaluation matrices, evaluation metrics, and decide if your model is good enough using these hyperparameters, and that's good for you. Then go the last step, which is reporting the data, the results, and here it is written validation. It means to validate your model on the test data, which should be a very separate data set that is to check for generalization and to avoid memorizing the training data. We refer to the overfitting term because it's very commonly used in machine learning literature, and it is just simply that the network is memorizing the training data and do not generalize at all. At the end, you present the data using plots, using graphical formats, using tables, and do your analysis. And this is to finalize the pipeline. So the pipeline that we discussed, we have four stages: pre-training, training, evaluation, and post-training. And we told you about the flexibility of the pipeline, because if you can look at these examples, what can pre-processing technique that can be used? You can do clamping, for example, setting the max pixel to some level or whatever, rescaling, rescaling the data to be from certain range or whatever, and so on. So this is pre-processing techniques. You can use one of them or none of them. If your data is already clean and pre-processed, then you don't want to invest time in this step. The same thing for the augmentation. You can do some geometric transformations, as I told you, or you can add some photometric transformations on the data as needed. And also you can use one or more or none in your pipeline. And then the data loading, which technique are you going to use? Sampling, you have larger training data and you are sampling some samples, put them on a batch and train, or using queuing because you'd like to use every some of them, or you divide the data based on the subject. And this is very important because in many cases, for example, if you are going to have these images for a patient and would like to see if he or she has caries or not. So you don't have one image for the subject. So you have many images for the same subject. So you can load the data in subject as subject level. And also it depends on your problem, you decide which model you're going to use. For segmentation, it's very common to use units. For classification, it's very common to use transformers. For detection, it's very common to use YOLO. And then you compute the output using what model you used and what problem you are working on. Will decide how is going to display your output using these activation functions. It depends also once you are sure about your problem, you can select which model you would like to use and what is the output format that you would like to generate, and the loss function that is suitable to this problem, and what is the optimization technique that is better suited for your problem. And also it depends on your problem, which evaluation metric is better for you for classification accuracy, and F1 score are good enough. For segmentation, we usually use DICE and IOU and HD95. For post-training, you use validation, either k-fold validation or post-validation or out-of-set validation. And finally, you display your results using one or more of these tools. So the flexibility of the pipeline allows you to interchange So in the training, I will use clamping. Next time, I will use crop or padding. Next time, I do this with augmentation or without augmentation. So you have many alternatives that are very open to you. So you can select which one is going to give you the expected outcome. So this is a good way to think about your problem as a pipeline, and every step in this pipeline is modular, and it can be actually it can also be customized. You can do your own pre-processing or your own augmentation or your own technique for training and so on. So this gives us the idea of pipelining an AI task. Okay, but what is very important for you as a researcher doing research on dentistry is to decide what is your input and what is your output. What is the input? The I refers to the input and the O refers to the output. Understanding the pipeline inputs and output is crucial for model performance. For example, if this is coming from a CBCT scan and would like to segment the ion nerve, then the points on the right, no, this is not ion nerve, this is the bulb. This is the bulb, then this will be the output that you are trying to find. The pixels that belongs to the bulb will be highlighted. So why this is very important? Because if you tell me this is your problem, I would like to see this input and get this output, I will tell you this problem is going to be solved using a segmentation algorithm. So once you know this problem is a segmentation algorithm, you decide which technique or which model is going to help you to do this segmentation. For example, UNets are very common in image segmentation, but also you can use different customized architecture from transformers and convolution networks and so on. So this is important to understand what is the input of your pipeline and what is the output, so that you can decide comfortably which architecture are you going to use. And also you can say, I'm going to decide which evaluation metric is very important for this task, because this is a segmentation task. Then you would like to compute the bias score or the intersection over union IOU. If you know the input and the output, you can take your decisions comfortably. What about the input?
Sorry, Professor, may I ask a question here, just to make sure that people are on the same wavelengths? Like you mentioned that this is a segmentation problem. Is it possible to explain what is the difference between segmentation and detection and these kind of problems? Thank you.
Okay. I think I have some other slides maybe later on this thing. Okay, let's see this slide now. So the classification task involving the categorization, medical images or specific regions within them into a predefined classes or labels. For example, you might have an image like this one, and you are going to ask me a binary question. Can you see caries in this image? Yes or no? Yes. Okay. So this is a binary classification task. Okay. But you can ask me another question. What is the highest level of severity you can see in this image? And you have three answers: mild, moderate, or severe. So if the image has caries, then you can ask another question. What is the highest level of severity you can see, mild, moderate, or severe? You will say moderate. So this is also a classification task. So the classification task is the task that you are asked about two or more classes that are present in the image. And then you decide if it is a binary class, yes or no question, or if it is multi-class classification, you decide which is the level of severity. Okay, this is for the classification. Another task, which is very important and very common, is the detection. And the detection task refers to the prediction of the bounding box around the object and give the label to this bounding box. Instead of giving a label to the whole image, you are giving a label for this bounding box. So for example, I'm asking the model to find the healthy surfaces. Then it will give me 1 box, 2 boxes, 3 boxes, 4 boxes, 5 boxes, 6 boxes. Okay, the model will return these boxes. If I'm asking the model to tell me which surfaces has mild or moderate carries, it will return 1 box. And if I'm asking if it has moderate or severe, maybe severe, I'm not sure. I'm not a doctor, by the way. So I think this refers to the severe one. Okay. So it will give you the whole, I'm sorry, all the boxes on all surfaces that have the severe carries. Okay. So the detection is not just one label for the whole image. It is a label for every detected box. Okay. Okay. And for the segmentation is to provide a pixel level labels. For example, you have these scans and you would like to find, I think this is the bulbs, that is our orange, I'm sorry, yellow. You would like to find the bulbs. So every pixel that belongs to the bulb should be returned. Okay. So this is one example for the segmentation task that I was going to give you a special session for the next webinar about the segmentation task.
So segmentation is like it gives it color codes the
pixels.
Yes, the thing that we are interested in, something like this.
Yes, for example, I'm looking for the bulb. Then I will give it training data which has some pixels labeled as bulb, and then at the tested time I'm going to give you an unlabeled image, and the model will give you where are the pixels that belong to the bulb.
Okay, and in your opinion, Professor, which one of the 3 tasks, classification, detection, and segmentation, is most common in dentistry or oral health, or are they the same? It depends.
Actually, it depends on the need, but I can tell that the segmentation is the hardest one because it works on pixel level. So, for example, in the image classification, you are giving one label for the whole image, so that's good. I mean, actually, we don't need it very much, so, because you need localized decisions as. For example, find the carries, not tell me there is carries or not. Tell me carries or not. This is very obvious for many non-experts. Maybe also might understand what is carries look like, and if you see, like to decide which pixels are belonging to a carries, or to decide what is the level of the severity of the carries on this box, which is a detection task. So I think detection and segmentation are more important. Classification should be much easier. And since it's much easier, it will be done as a side product. So you can always transform the results from the detection to answer your classification questions. You can find also the same thing about the segmentation.
Okay, thank you.
Did this answer your question, Professor?
Yes, it does. Yes, thank you.
Okay, yes, yeah, we stopped here about the input modalities. Modality refer, and this is very important actually. This one is very important because not the data is not coming in the same format from every sensor, and also depends on the case that you are working on. Some people are working in one modality, some people can obtain multiple modalities. So what we mean by modality here, for example, this is called panorama X-ray, and this is modality, and this is coming from CBCT. This is another modality, and this is coming from intraoral camera, and this is a third modality. We can also find the reports, or we can find comments from the dentist who is examining the patient. We can have videos coming from the intraoral scanners as well. So the modality also guides the researcher which technique that is going to be used. For example, techniques that is using 2D images might not be suitable to work on 3D data, or you're going to make slices from the 3D data to make it like 2D data, but this is not good enough. I mean, if you are working with 3D data, you can find better results if you are going to work with 3D models that is respecting the 3D structure from the data. Okay, and there are also some other tasks I'm not including here in this presentation or the second section. Creating synthetic data. Creating synthetic data, this is not just about augmentation. You can create synthetic data like you can get the impression that they are coming from the CBCT scanner, but they are not coming from CBCT scanner. So this is different from the augmentation, and I didn't include it because this is, and it has to be discussed as standalone topic. Synthetic data generation is also another important problem. In addition to the classification, detection, and segmentation, the synthetic data generation to give you the data that looks like coming from the sensors that you are already using. This is very interesting task. Okay, so once you are having the sensor that gives you the data, for example, you are working on panorama X-rays. So this is called the unimodal input because you are only using a single modality. But in some cases, you might be able to obtain multiple modalities. For example, you can have CBCTs plus panorama or CBCT plus text reports or any combination of these models. And interestingly, the modality combination, if you can have multiple modalities, I mean, you can have stronger results, but you are adding more complexity to the neural network, the architecture that I'm going to develop. Okay. What is also very important about the input to understand what is the dimensionality. So we often refer to the dimensionality about most of the time about the spatial. So the image is like 1000 width times 1000 height, something like this. But this is not the only dimension that we can work with in the data, because, for example, if you are having a video, then you have spatial dimensions plus temporal dimensions. And also, if you can work on, for example, different wavelengths, this will give you multispectral CTs, for example. So it is not just about the spatial XY dimensions. For example, you might have XY dimension height width, you might have 3 dimensions like CT and CBCT, and also might have spectral dimensions, or might have time dimension. So as long as you are very sure about the type of data you are going to process, this will affect your decisions on which models you are going to apply with them. So for example, this on the top we see a volume. This is 3D volume. We have ground truth annotation for the bulbs, and also we have ground truth annotation for the nerve, and this data comes in 3D. How are you going to work on the data that's coming in 3D? Then you have to work with models that work on 3D data, or you can do slices and work on the slices which will be 2D data in this case.
Please,
So,
Professor, what does ground truth mean?
this is the labels that the model learn from. So, for example, you have 500 cases, and you would like to estimate where can you find the nerve or the bulb, for example. So the model doesn't know where to find the bulb or to find the nerve. Then the training data must be accompanied with the labels. So these voxels, in this case, it's not pixels anymore. These voxels refer to the nerve, and we color them in a red color. Who is going to do this? The annotator must be a specialized doctor that can use software for example, TK Snap. I don't remember what the other one. Maybe what was the other one?
Yes, this like our annotation software or platforms, right?
Yeah, you must do this. You have to do this. The researcher must do this, or the other solution is to work on publicly available data. The public there are some data available for example, for the nerve. There are some data set called the Tooth Fairy. They have like 500 volumes. They are annotated with this annotation for the nerve and maybe also the hard tooth structure and so on. So, but the most important thing is if you are training on one single source from the data sets, the generalization will be questionable. You might not be able to generalize enough. So it is always a good idea to have data from your own machine that is you are going to work on. So that's very important. So that will give you this role. You have to annotate the data.
So what you're saying, Professor, is that it is better to use like local data from the same population to produce the models, right?
We have two things to think about. The first thing is to collect my own data from local distribution and do everything on it, okay? But in many cases, you are not allowed to get 100 cases. You know, I just have like 50 cases. So your model will be weak in this case. So the best thing is to learn from large available data and to fine-tune your models on the locally collected data. This will give you the best results according to my experience.
Yes, sure. And to fine-tune on the locally collected data, you need to get like the image, whether it is an intraoral image or an X-ray or a CBCT or whatever, and do this annotation, which is marking the thing that I'm interested in, whether it is pulp or nerve, and labeling, like giving it a name.
Yes, bulb or nerve is an example. Maybe someone is looking for maybe some defect or artifact of a special shape in the volume. So this is just for example, but it depends on the case you are studying. Maybe someone is working with, for example, segmenting abscess or something like this. So you understand what I mean. This is just for example, but you have to work on your own problem, collect your own data, annotate your own data. This must be done. Okay.
Okay, and how many would I need if I am going to work on already existing data, then fine tune on my own data? Like how many of my own need I to collect?
Also, this depends on the modality. For example, it is very easy to find panorama X-rays, right?
Yeah.
But it's very hard to find CBCTs for children, maybe. So this is a very hard. So what I'm going to say in my answer is this. If you are working with 2D images, then bring as much as possible, 1,000, 2,000, if less, 500, no less than this.
Okay, these are like whole X-rays, like the one below the panorama below is one, not, it is not per tooth, I mean, right?
No, per one, per person. Yeah.
Okay. Yes, thank you.
But for example, if we have done some very good results on 127 CBCTs for BIDO for segmenting the tooth in a mixed dentition scenarios. We just had like 127 cases and we find good results, but it was 3D. It was CBCT, not 2D. 2D is easy to find. Actually, there are many data sets. For example, I had one of my master's students in Alexander University worked on like 1,600 panorama X-rays. So X-rays
I'm curious. I mean, if you can manage to develop a good model with like 127
volumes,
but you need for 2D you need like thousands. Is this like depending on the
okay, let me tell you also another thing. What is the level, what is the expectation from the model? If you are giving a simple modality, then you are expecting very high accuracy, right? If you are giving difficult modalities, then you don't expect the same. So for example, if you obtained in the above image IOU around 80, then you're more than happy. More than happy.
This is like accuracy, an accuracy of 80?
Yeah, evaluation metric, yeah.
Yes.
But here, if you would like to find the carries in this image, for example, and you say my accuracy is 80%, no, this is not acceptable. You see?
Okay. Okay. So it depends on what is your aim, what thing you are training the model for, and stuff like this.
Right.
Not only the type of the input, like whether this is a 3D or 2D.
Yes.
Okay. Okay.
Yeah, and also it is very important to review the literature and to see if the results that already obtained on smaller data sets are good enough. Then this will give you, okay, they worked on 127 CBCTs mixed dentition, and we obtained the results. That is good. So then you can use this as a guideline for your problem if you are going to work on mixed dentition as well. You understand what I mean? And also, there is one important thing. If you are able to collect more data while you are developing your models, this is a good idea. For example, you have your initial expectations that I need 1,000 images. But when I trained my model on the training data of the one, for example, 600 images from 1,000 images and tested on 200 of them, I found my model is doing like 75%. If you have the time and the availability for resources to collect more data, the best thing to get better results is to increase the data. Okay, if you are sure about your selection for the models, if you are sure about the quality of the models that you are using, the most straightforward approach to increase your results is to add more data. Okay, with correct annotations. The data must be accompanied with annotations.
Yes, I want to ask also a question about the annotation and labeling here. Now, if you're going to work on 1,000 panoramas, it would be very difficult to have like one researcher or one person working on all this, like annotating, which is like marking boxes or whatever, and labeling.
Exactly right. I will tell you one other approach for annotating the data is not to start from scratch.
Okay.
So, for example, in one paper, I worked on CBCTs for hard tooth structure segmentation. We started with 12 scans only. We didn't have more than 12 scans annotated. We just had this annotation for 12 scans. And then we learned a model that is good based on the 12 scans. And then we had like 100 scans. We just produced annotations using the output of the model on the remaining 100 scans. And then we returned the scans with the annotations the model is giving to the annotators again. And then the effort they have done on this phase is much less than the effort they have done in the first initial phase, where they started with 12 volumes without any labels. So you can do this in like iterative refinement, and this is called active learning in the machine learning. They call it active learning. You start with few correct samples, you generate incorrect annotations, return the incorrect annotations to the annotators. They will produce more accurate annotation in much lesser time.
Yes, okay, good. So another question, please, Professor, because most of the people here are like dentists who are not going to be doing the model themselves, but they will be on the other side, like data collecting, labeling, and annotating and stuff like this. Is it possible to do this like using commercial software, and are there free
There
or
are there are
yeah?
some good software. Maybe RoboFlow is good, but it's very expensive.
Okay.
Beyond, yeah. And also there might be another solutions, but and also there might be some other companies providing this kind of task to produce models, but it will be paid. To train your model, definitely it is not a straightforward task for dentist, for a researcher doing his research from dentistry background. And also this might allow some chances for collaboration. But
Yes.
I am very sure that if you have budget good enough, then you can go for some commercial solutions.
So do you think it
So it
is
also depends
possible?
on you.
Yeah. Do you think it is possible for like a network of researchers to be collecting data that would be considered the input for a model, like a unified model, and people are collecting input data on their own in different places, and maybe like calibrating on annotation and labeling, and then the AI experts like yourself or young people from your lab, they can develop the model based on this. Is this kind of collaboration possible?
Yes, of course. Yes, we also we encourage this kind of collaboration. But I mean, there is some for the collaboration to be successful, the tasks need to be well defined. So the data collection, data annotation, this task should be totally agreed on, because from my experience, that at some point of time, if the annotation is not calibrated between the researchers, the model will suffer. So, for example, some researchers sees this is moderate, but other one says no, this is not moderate, this is just mild. So if there are some discrepancies, the model actually might not
Yes.
be able to find the correct thing. But the solution for this again is to provide large data. So if the data has noise, but it is large enough, the model will learn better than individual researchers.
Noise is errors.
Yeah. Yeah,
Okay.
actually, if you have large data with noisy labels, the model will learn still.
Yeah. So my question, noisy labels means labels with errors, like I misclassify the
Yes,
caries
yes.
stage and such
For
stuff like
example,
this.
yeah. If it is carriers, you misclassified samples. But for example, if you are working on voxels, you missed some voxels for non-ion and you call it ion or the reverse. So I am saying if you are having large data, the mistakes, the noisy labels that are within some tolerance, of course, is not going to hurt the model learning process.
Okay.
As long as you have large data, but the problem is that, how many cases you have in your hand now? And actually, I found some very strange behavior from many dentist researchers, that they are throwing their data. They are not keeping the data. So, for example, you might find many researchers. Okay, did I needed to free some space from the device, so I erased the old scans I had. So this is very common actually for the medical
Yes.
researchers. Yeah.
Yes. I can
Yeah.
understand. Yes.
Yeah. So yeah. Uh, the last thing I'm going to tell you about today, I was very optimistic, and I I had two sections, but the time is not going to allow me actually. I will just stop at I finish this section one, and I can share the slides with you, but next time I'm going to speak about especially the segmentation task. What is the output? The output constitutes the task definition. If you know what is your output, then you will be able to define the task. As we have seen here, it is classification, segmentation, or whatever task you would like we work on. Uh, This is for the internal representation. If you're going to train model or whatever, you need to understand what is the representation is going to be stored in the machine and so. So we refer to every data holding structure as tensor. The data holding structure, we name it as a tensor. The tensor rank is different. If you have one number, we call it a scalar. If you have a set of numbers, we call it a vector. If we have a 2D array of numbers, we call it matrix. And also we can have more than 2D arrays. You have 3D volumes, we call it also. Every one of them is called a tensor. This is one tensor, one by one tensor, and this is 1D tensor, this is 2D tensor, this is 3D tensor. Actually, we use the tensors to represent the data, actually. For example, if you have a volume, and these are the segmentations, ground truth, the labels, I mean, for the ion and for the bulk. So it seems that these labels should be stored in a tensor structure. So this can be used, but since again the job of the training the models doesn't apply to the listeners here or the audience here, so this is not very important thing. But the most important part is this slide to define what is your task. Is it classification, detection, or segmentation? These are the most common tasks that I worked on. Actually, I have like maybe 10 publications in dental domain, and these are the most common tasks that I worked on, either segmentation, classification, or detection. Okay. This was the second section, but I will stop here for the to receive some questions from the audience. Thank you.
Thank you, Professor. Thank you very much for the comprehensive presentation, and I'm sure it may be like a large bite to swallow, but we'll get familiar with the terms and the language and the concepts and all this. So for those attending, any questions? Any questions that you'd like to ask, any clarification, any thoughts that you'd like to share, or points that you'd like to raise? Any thoughts? Maybe this has all been in computer vision. Maybe you would like to have some questions, general questions that are not related to computer vision that we can ask Professor Torki about, or keep to the next session, or anything about what we have been discussing today. So any questions? Okay.
Okay, inshallah, next week, next time, I mean, no, Thursday, we'll take one special case, which is the image segmentation, and we'll give a more detailed presentation on this task only. And this one, inshallah, we'll give you some useful,
practical applications on it. Yes. Thank you very much. Thank you very much, Professor Torki, for the presentation and comprehensive overview of the pipeline. And thanks for the AFRONE attendees. And we meet for the second part of the presentation on Thursday at 5 p.m. Egypt time. Thank you very much, and have a great evening. Bye. Bye.
Bye. Bye.